Hi, I'm Kara. Joel and I are going to be walking through our design process for the portable oxygen consumption calorimeter we built this year. So our sponsor, Dr. Richard Emberley, tasked us with building a portable oxygen consumption calorimeter in order to measure the heat release rate of a burning substance. So this type of calorimeter works by measuring the byproducts of a fire, and specifically we measure the carbon monoxide, carbon dioxide, and oxygen concentrations of the incoming air when we're burning a substance. And so our goals were to reduce the size and cost of the oxygen consumption calorimeter while also maintaining our system accuracy. And so we focused on using cheaper and lighter parts compared to current oxygen consumption calorimeters that are on the market. So our system overview. So this is an isometric view of our CAD model. So we have a 12-volt power supply right here that powers our pump, our oxygen sensor, as well as our CO2 sensor. And then we have this inlet hose that extracts the air from this exhaust duct that's in the combustion lab at Cal Poly. And on the next slide, I'll show the specifics of that. But so we come through our inlet hose and then we go to an air filter, and then that filters out the soot particles. And then we have our pump, which pumps the flow through. And then we go through our measuring devices, so our O2 and our CO2 sensors. And then we have our outlet, which goes back up to the exhaust pipe. And so we have these little thumb screws that screw down into our briefcase. So this whole design goes into this briefcase right here. And this is our actual final build right here. And so the thumb screws lock down the acrylic plate into the briefcase so that when you are moving or transporting the device, our components don't fall out or get displaced. And then we have these little feet on the bottom just so that the connections and components that are underneath, those straps aren't like touching the ground or dragging. And so that device connects up to our exhaust pipe here. So this is in the combustion lab at Cal Poly. And so you would burn your substance underneath this fume hood, so somewhere down here. And then the smoke that's coming up from that, the fume hood directs it into the exhaust. And so these fittings here are what we're gonna actually connect to. So this is the exhaust pipe here. And so we're just putting barbed fittings onto the exhaust pipe, and those hoses that we saw in the isometric view, those just connect up right here. And then, as I mentioned before, we have our power supply, which powers our pump and our CO2 sensor. And then our oxygen sensor connects directly to our CO2 sensor. And then from our CO2 sensor, that has a breakout board. And there's an RS-232 connector that we have that goes to a USB, which plugs into your computer. And so on your computer, we have our GUI. And so the features that we have here is we're plotting the heat release rate against time, at like the current time. And the table above it shows like the current output values of the time, the heat release rate, and concentrations for our 3 gases. And then the little button light indicator that's up in the left-hand corner that says COM3 connected, that's just to let you know. It'll turn green if your sensor is connected into the right COM port. And then the run button runs the code, starts the plotting process. And then when you press stop, it'll stop collecting data, and it will store all the data into an Excel sheet for the user to use that information afterwards for post-processing data if they would so like to.
Thanks, Kara. And this is the design process that we went through over the entire year of the senior project. It began with the brainstorming and ideation phase. We decided what the boundary diagram of the system was going to be, and then it moved on to selecting the sensors and CO2 sensor, preferably an integrated sensor, making it much simpler for the coding side of the project, and then an oxygen sensor. Also, we had to select other hardware components, pumps, hoses, battery, and briefcase, and I'll describe more into how we selected those on the next slide. Also, then we had to design the CAD model with those components of the system. Uh, and moving on to after that, we had to machine the components. Essentially, we had to machine the acrylic base plate. We laser cut that with in the Cal Poly machine shops, and then we moved on to testing. And in there, we went into SPL labs in the electrical engineering building at Cal Poly, and set up the testing equipment for our sensor, connected to power supply, and then connected to the computer and ran testing. Uh, then we moved on to building and assembling the device. And actually, we kind of went back and forth between the testing and building and assembling, because we found a problem or found a thing that needed solving, whether it was wires that weren't working properly or components that weren't talking to each other correctly. Then we had to go to building and assembling a new type of component or a new fastener or a new type of wire, and then going back to the testing. And then after we're done all of that cyclical process there, then we had to program the GUI to work properly. And yeah. And component selection. So the 7911 Crestline sensor was recommended by Professor Emberley, and the integrated sensor was more expensive, so it was a little harder to find one that was within our budget, but we did, and that's why we selected the one that we did there. Then talking with Crestline, who made the CO and CO2 sensor, we found a compatible oxygen sensor, which is the AO2 oxygen sensor, which is why we selected that one, because compatibility was a big concern, whether they would work together, they would talk to each other properly. So we wanted to do that properly. Then we selected a pump, which had the correct flow rate for the sensor. The CO2 sensor has to have a flow rate through it has a max and a min flow rate for its integrated sensing. And we wanted to make sure that that was within the range, and that's why we selected the pump that we did. It was a 12 volt pump. And then we selected a 12 volt bio-NO power supply because it had two cables, one for connecting to the system and then one for charging. So we actually don't need to disconnect anything to charge the battery. We just need to connect the charging cable there. Also, it has a 14-hour life, which is very good for the portability of the system. Then we selected the hose because it was rated for the temperatures that we were expecting, actually rated much higher than the temperatures we were expecting for the exhaust. So we have a factor of safety there. Selecting the Wattman 67235,000 HEPA vent filter, quite a word there, but we selected it because the filter had a size of 0.3 microns, meaning it could filter anything above 0.3 microns. And in our research that we did, we found that 90% of smoke is about 1 micron in diameter. So this would filter approximately 90% of the smoke, making sure that we don't have to clean the sensors or they get clogged up or the pump has problems. This is to ensure that the safety of the entire calorimeter is properly assured. And then we selected the briefcase because it'll provide proper protection for all of the components. It's supposed to be portable, so we want to make sure that it can be portable and without having a large risk of it being fragile and dropping or breaking any of the components. Design verification. The initial testing of the Crestline CO and CO2 sensor was in the SPL lab at Cal Poly. You can see there's the power supply that's connected to the CO2 sensor, and which is then connected to the computer there running the code from Crestline. And we wanted to make sure that it ran properly, and that was more in the testing phase, ensuring that our design worked properly. Then we used the data from previous tests, which Professor Emberley provided to us. It gave the heat release rate and the oxygen concentrations, the CO2 concentrations, and the CO concentrations, as well as the heat release rate, and we could actually compare it. We could run it through our software and compare it to the actual values and make sure that we were reading that the GUI was running properly. Uh, we would have done normally we would have done this by actually doing a test in the lab, but we due to COVID-19 we didn't have that option. A lot of debugging sessions with the software and the GUI and user testing, ensuring that it properly fulfilled the requirements that our sponsor was looking for. Um, and because of the coronavirus, we had to do some tests that we are not capable of doing right now that we would like to do in the future. A calibration test of the calorimeter, where you have known concentrations of gases that you run through the system and compare it to actual readouts and calibrate it properly. And we also like to compare to a known heat release rate. So we would actually burn a substance in the fume hood, measure it, and compare it with the calorimeter and the known value. But unfortunately, we can't do that now. Also, we need to do flow rate testing and the life cycle of the filters to ensure that the system is running properly and that it can run properly in the future. And yeah, in conclusion, on the left, you can see an image of our calorimeter hooked up to the computer, and it's a little difficult to see, but there's the GUI is up there with the MATLAB code running, and it's all working properly. And on the right is the calorimeter inside of the briefcase, and it shows the kind of the entire layout of the system. Uh, so the design met its specifications of being under $3,000, and as well as it's portable. It's only weighs 12 pounds, and it's within the correct dimensions that we specified. Um, some major challenges we had over this entire project was uh, finding a CO and CO2 sensor that was within our budget, because we wanted an integrated sensor, as I mentioned before, but that there's a lot of problems with having three separate sensors rather than just two, compatibility issues. But a lot of the CO and CO2 integrated sensors were very expensive and not within our budget. So that was a big challenge. Also using the app designer in MATLAB to make the GUI, there was a learning curve, but I feel like we did fairly well there. Overall takeaways from the senior project is we learned a lot about the field of fire research and fire design, and as well as fire safety, learning what the importance of the heat release rate value is in designing sprinkler systems and proper understanding of fireproof materials, to make sure that the safety of all these designs are done properly. Also, we learned a lot about the design process from start to finish, ideation to completion. It was a great learning experience. Learned a lot about teamwork, proper communication, risk and safety analysis, as well as talking with suppliers, which is very important in the work industry. And I feel like we had a useful and proper, great learning experience, and that was something to be proud of. Thanks for watching.